Here we talk about a very strong clause in mathematics, and that is that differentiability implies continuity. If a function is differentiable at a point, then the function is also continuous at that point. Because the clause here for differentiability is a stronger clause than continuity. Differentiability includes within it continuity. So here, if this statement is true, which it is, and it's provable, then the contrapositive of this statement is also true. And the contrapositive simply says that of this statement here, that if a function is not continuous at a point, then that function is also not differentiable at that point. So we can use that to show that a function may have partial derivatives existing, but that function might not be continuous. And if it's not continuous, then that it concludes that the function is not differentiable at the particular point. Saying that the partial derivatives exist does not mean that the function is differentiable at that same point. So let's see. So here we want to show that the partial derivatives exist. So the partial derivative of f with respect to x by definition is the limit as delta x goes to 0 of f of here, x naught and y naught are 0, so this is 0 plus delta x comma 0 minus f of 0 comma 0. This is all over delta x. So this is, yes, the limit as delta x goes to 0. You evaluate this function f of delta x comma 0. Well, that gives us 0. And then minus f of 0 comma 0, that's 0. And this is all over delta x. So we get the limit of 0 divided by delta x, and that's 0. Because 0 is already at 0, delta x is traveling to get to 0. So we're not dividing 0 divided by 0. Not just yet. It takes a while for that to happen. So to talk about calculus is to talk about the process. It's not to talk about like the algebra where you're right at the point already. So now the partial of f with respect to y at 0 comma 0 is the limit here as delta y goes to 0 of f of 0, which is x comma y plus delta y, but y is said to be 0, plus delta y. This is minus f of 0 comma 0. This is all over delta y. We get the limit as delta y goes to 0, and here we get 0 divided by delta y, we get 0. So the partial derivatives based on this piecewise function, the partial derivatives exist, but does that imply continuity? No, it does not, because saying that the function's partial derivatives exist does not say that the function is differentiable totally. Let's see. So here we examine continuity. So to examine continuity, we find the limit of the function as we travel from various segments to get to the so-called origin, if you will. So here we can look at the limit here. I want to examine this along the line y equal to x. I reckon I should state that. Consider the limit, and here the trace along the path y equal to x. So then this is the limit here as x comma x gets close and close to the origin of that particular function there. So this is 5x squared y all over x cubed plus y cubed. So this is the limit as x comma x approaches the origin. Just replace y with x. So this is 5x to the third all over x cubed plus x cubed is 2x cubed. The x cubes cancel. We have the limit of a constant is a constant. So all the limits for the function to be continuous, all the limits depending on, it doesn't matter how you get to the origin, but as long as you get there, all the limits are supposed to be the same thing. So now we consider the limit in the trace along the path. Here I will look at along the path of y equal to x squared. The parabola is in there of the 5x cubed y. I mean, you can even trace along the hyperbola as well. You have several traces going on within this graph. So this is the limit here, x comma x squared gets close and close to 0. We're looking at 5x squared y all over x cubed plus y cubed. So this is the limit as x comma x squared gets close and close to 0. So here we're going to replace the y with x squared. So this gives us up top 5x squared times x squared. So we get x to the fourth. This is all over x to the third plus y to the third, which becomes, the y becomes x squared. So this is x squared to the third. So this is the limit as x comma x squared gets close to the origin. Up top we have 5x to the fourth. Downstairs we have x cubed plus x to the sixth. I'm going to factor out of x cubed. So this is 1 plus x to the third. And this is the limit as x comma x squared gets close to the origin. Up top we have 5x. Down below we have 1 plus x to the third. Now as x goes to 0, then this whole limit here goes to 0. Right? We get 0 over divided by 1. But we get different terms. Up here we get this limit, and there we get this limit 0. They're not the same. You remember from calculus 1 that we talked about the left-sided limit must equal the right-sided limit, you know, for showing that the limit at that particular function exists. Basically, you were showing and proving continuity. But in calculus 1 is only one dimension. You're only talking about the x-axis, looking at from the left side to the right side. Here in calculus 2, we're talking about several dimensions because you have z, which depends on x and y. So you're looking at what's happening in the plane, and then even in a higher sense, you're looking at what's happening in the space. So if you have a point under investigation, and if I'm traveling this way, or if I'm traveling that way, if I'm coming from down here, from down in Sheba, or if I'm coming from the east, if I'm coming from over there, then I should end up at the same point. But when I do that, tracing the different paths, here I get 5 halves, and over here I get 0. So I come here and I get this point, then up here I get some other point, and then they're not the same, so they're not continuous. So this function is not continuous, and by the contrapositive, if the function is not continuous, if a function is not continuous, then the function is also not differentiable at that point. So I believe here you've just shown that this piecewise function, even though the partial derivatives exist, the function is not differentiable because the function is not continuous at the point 0, 0.